Hello, today we're going to talk about calculating equilibrium concentrations. This will focus mostly on ice charts. So what is an ice chart? An ice chart is where we're going to track the course of an equilibrium reaction. So let's say, for example, we have, hydrogen and oxygen forming water. We always write the reaction at the top, and then you will have a table of values. Okay, and so you will do 3 rows, I, C, and E, initial, change, and equilibrium. So, and then you will plug in the initial values that they give you or the equilibrium values that they give you. And then you're going to use the coefficients from the balanced chemical equation to show the change. Now, more often than not, they'll give you an amount of reactants and no products, but it doesn't matter what it is. If they give you some amount, there will be some change. If the reaction is going to proceed in the forward direction to reach equilibrium, then the products will increase and the reactants will decrease. And the reactants will decrease stoichiometrically, which means according to their coefficient. So this will go down by 2x, and oxygen will go down by just x. Then on the product side, the water will increase by 2x. So you always use those coefficients. Now, the opposite is also true. If the reaction has to proceed in the reverse direction to reach equilibrium, then the reactants will both increase and the products will decrease to reach equilibrium, but it will still follow the same stoichiometry. Now, a couple things here. Ice charts, you always want to plug in concentration in molarity, because those are the values that we would use in a Kc expression, and products over reactants. Or you could do pressure in ATM, because those are the values that you would use for Kp. So you do the pressure of the products over the pressure of the reactants. Coefficients become exponents. But you always want to use molarity or ATM, depending on the scenario. Of course, if you have any solids or liquids in your equilibrium, you don't include solids or liquids in your equilibrium expression. So you would not include them in your ice chart either. So if we were to do this a little bit differently and instead make liquid water, all right, the liquid water is not part of our equilibrium expression. So you would not include this column. You would just look at what is increasing on the reactant side if it's going in the reverse reaction. But again, that's fairly rare, I would say. Just make sure that you're ignoring the liquids and solids. They still need to be there. They're just not affecting your equilibrium position. So let's look at how we would use ice charts. So they given the reaction A plus 2B yields 4C. If your initial concentration of A and B is 1 molar and the equilibrium concentration of C is 0.12 molar, what is the value for Kc? It's a very typical equilibrium question. Okay, initial concentration of A and B is 1 molar. If they don't tell you that you're starting out with something, you can assume that the initial amount is 0. So I'm going to go ahead and plug in 0 for C. Notice that they included the coefficients in the actual ice chart. Some people call these rice charts because you should put the reaction at the top, but I like the word ice chart. It sounds better. Those are all the things that we know just from reading the question. We also know that in order to go from 0 C to 0.12 concentration for C, this side must increase. So we know that the reaction must proceed in the forward direction. So the products must be increasing and the reactants must be decreasing. Then you fill in the coefficients to figure out how much it increases or decreases. A goes down by just 1x, B goes down by 2x. C must go up by 4x because of that coefficient of 4. So now, if we look at the C column, everything is filled in on the C column. We have a 0 plus 4x equals, remember equilibrium equals, 0.12. We can solve for x. So x is equal to 0.03. Okay, now that we know x, we can plug in x for the other substances. You would plug in 0.003 for A, and then 0.03 for A, and 0.06 for B, because it's twice as big. So let's go ahead and do that. So 1 molar minus 0.03 is 0.970, and then 1 minus 2 times 0.03 gives us 0.940 for the concentration of B. Now that we've plugged X back into our ice chart, now it's time to use Kc. And you should write your equilibrium expression. Kc is equal to the products over the reactants. So it's C to the 4th over A times B squared. And so we need to plug in our values. C is 0.12, and you will raise that to the 4th power. A is 0.97, and B is 0.94 squared. And when you plug all of those numbers in, you get 2.42 times 10 to the negative 4, which means it favors the reactants, which we can see there's more reactants than products. There's no there's no unit for K, it's just a ratio. So here's another example. A plus B yields AB with an equilibrium constant of 3.4 times 10 to the negative 3. They gave us the value of the equilibrium constant. Okay, so this one's going to be just a little bit different. So that if we add 1 molar of A and 2 molar of B are allowed to reach equilibrium, what are the equilibrium values? So they didn't tell us there was any B to begin with, so we can plug in the 0 there. Then we need to think about the change. You can't have a negative amount of a substance, so the products must increase, which means the reactants must decrease. And the coefficients are all 1, which is nice. So this goes down by x, this goes down by x, this goes up by x. Now for this one, they didn't give us any values at equilibrium, so we can't solve for that row yet. For right now, let's go ahead and just plug in, this is 1 minus x, this is 2 minus x, and this one's just x. Now we need to use our equilibrium expression. I'm going to write it over here in the purple. So Kc equals, we have AB, products on the top, reactants on the bottom, A times B. And then we know they gave us the value of K. K is 3.4 times 10 to the negative 3. We also know AB must be just x. A is 1 minus x, and B is 2 minus x. So there's a couple things that you can do here. I recommend that you use a graphing calculator. There's a couple different ways you can do that as well, but you're going to need to solve for x. I don't recommend factoring everything out and using the quadratic equation. That's going to take a lot of effort, especially for the AP exam. So you just want to look at how you can easily solve this using your calculator. And because the AP Chemistry exam now allows calculators on the whole entire test, it makes it very straightforward if you have a graphing calculator. One way that I like to show my students, because it seems to kind of click in their brains, is that I try to get rid of fractions. So we do 3.4 times 10 to the negative 3 times 1 minus x times 2 minus x equals x. And then in your graphing calculator, you would do y equals this side of the equation, and then you would do y equals this side of the equation. And you will get two different graphs, two different lines on your graph. And you just need to find the intersect of those two lines. And when you find the intersect, that will give you the value of x that makes this true. I think that that's probably the way that more students will understand how to do it. There's also some calculators that will have a solver function where you can plug in and actually it'll solve the equation for you. So that's a possibility as well. But I like to use the graph function because it's a very visual and easy way to see that this is what makes the value true. So if we do all of that, we will find that x is equal to 0.0067 for x, okay? Then what you need to do is plug that x value back into your ICE chart to find the equilibrium values for each of those things. So when you do that, I'll write it up at the top, you would do 1 minus 0.0067 will give you the value for A, which is just about 0.99 with 2 sig figs. For B, you'll do 2 minus 0.0067 and you'll get just about 1.99 for the concentration of B. And then C is just X, so that's the 0.0067 molar for C. And so that's how you solve those. And these ones tend to be a little bit more rare than the previous example, just because it involves a little bit more work. Okay, so this time they're giving us the reaction, and we don't know Kp. You should always write your ICE chart, I2 plus Cl2, 2ICl, and they're all gases. And then so remember ICE, ICE chart. And they tell us that enough ICl is added to reach a partial pressure of 2.45 atm. You can use molarity or atm in ICE charts. Right. And it says it was in a previously evacuated vessel, so we know we don't have any I2 or Cl2 to begin with. After the reaction reached equilibrium, the pressure of the I2 was 0.3 atm. Complete an ICE diagram complete the ICE diagram to find the equilibrium pressures of each species and use those values to calculate the value of the equilibrium constant. There's a couple extra words in there that we don't need. But anyway, we know that the reactants must increase because they're currently at 0, and the products must decrease. And then we use the coefficients, so I2 increases by x, Cl2 increases by x, ICl decreases by 2x. So the I2 column is complete. 0 plus x equals 0.3. So I know that x is 0.3, which is nice. So I can go ahead and fill in the Cl2 column, which should be the same because it has the same coefficient. And then for ICl, you'll solve it's 2.45 minus 2x, or minus 2 times 0.3. And that will give us 1.85 atm. Now we can go ahead and write our Kp expression. And remember, pressures, you want to use partial pressure notation. So the pressure of ICl squared all over the pressure of I2 times the pressure of Cl2. And when we plug in those numbers, 1.85 squared over 0.3 times 0.3. And then you can solve for Kp, which is 38. Okay, in our last example, we have N2O4 gas going into 2NO2, and we don't know the Kp value, but we're writing our ICE chart here. And it says the reaction mixture initially contains a partial pressure of NO2 of 0.1 atm. When the reaction reached equilibrium, the partial pressure of NO2 is 0.08 atm. Find the equilibrium concentrations and use it to find the value for the equilibrium constant. So we don't have any N2O4 to begin with, so we know that reactants must increase and the products must decrease. And we plug in our coefficients, so plus x minus 2x. We can solve the NO2 column now. 0.1 minus 2x equals 0.08. So it goes down by 0.02, so x must be 0.01. Now we can go ahead and write our Kp expression. The pressure of NO2 squared over the pressure of N2O4. And so the pressure of NO2 is 0.08 squared over the N2O4 is 0.01. And when we solve, we get 0.64 is our value for Kp.